Okay, hi, I'm Sammy.
And I'm Amaya.
And for our research, we have chosen to study Hopfield Networks. We're both interested in neurology and the ways in which memories are stored in the brain.
Therefore, in this presentation, we have decided to explore the Hopfield networks and their relationship with the brain's memory storage system. To start, we're going to talk about arguably the most important neuroscience patient in history. His historical record allowed scientists to gain the first clear evidence of how brain structure is related to memory.
His name was Henry Molassen, also known as HM. He had severe epilepsy in 1953, so surgeons removed large parts of his hippocampus to stop his seizures. After the surgery, he couldn't form any new long-term memories, but he still remembered things from before the operation and could learn new motor skills like riding a bike. This showed that the hippocampus is essential for turning short-term thoughts into long-term memory, but isn't needed for motor memory. The hippocampus is a crucial part of the brain in order to understand and create and maintain memories. In the image on the left, you can see how a normal brain looks, and on the right, you can see how HM's brains look without the hippocampus.
There are multiple types of memory in the brain. There's sensory memory, short-term memory, and long-term memory. Sensory memory briefly holds sensory information like sight or smell just long enough for the brain to notice and decide if it's important. It is stored in the brain's sensory cortex, as shown in the picture here. And the information then moves to short-term memory while unintended data is lost. Short-term memory is stored in the prefrontal cortex. It temporarily holds information a person's actively using. If rehearsed, the brain strengthens it and restores it permanently as long-term memory. Long-term memories are formed in the hippocampus. Some information may be lost over time, but the cerebral cortex holds the information, mainly permanent, allowing us to recall past experiences, knowledge, and skills whenever needed. All of these memories revolve around one scientific principle, the Hopfield network.
Hopfield networks store and recall patterns much like human memory. During training, the network learns specific patterns, including images or words. Later, when given a partial or slightly altered version of a pattern, the network recognizes and completes the pattern accurately. This ability makes Hopfield networks useful for tasks such as error correction and pattern recognition.
Continue from where we stopped at, which is the memories are stored in landscape and what are Hopfield networks. So a network reaches a stable state by minimizing an energy function, right? So which measures how close the current state is to the stored memory. This process resembles a ball rolling down into a valley and settling at the lowest point as shown in the picture. And this method is called gradient descent. The lowest point represents a learned memory. Because of this behavior, Hopfield networks earn the name associative memories and linking incomplete or noisy inputs to the complete and correct outputs. Now, the picture on the right shows the winners of the 2024 Nobel Prize in Physics, John Hopfield and Geoffrey Hinton, who used Hopfield networks to make important contributions to machine learning, the foundation of modern AI.
However, in order to really understand Hopfield networks, a network that memorizes patterns, how is it done in the brain? In order to understand this, we need to know what synapses are. Synapses are the link between two neurons where they communicate with one another. Synaptic transmission is the process of which neurons communicate with each other. When a neuron receives a signal, it generates an electrical impulse called an action potential, which travels down this axon into the axon terminal. At the axon terminal, the electrical signal triggers the synapses and releases chemical messengers called neurotransmitters into the synaptic cleft, a tiny gap between the neurons. These neurotransmitters cross the synaptic cleft and bind to receptors on the surface of the neuron, initiating a response. This process allows the signal to be transmitted from one neuron to another, enabling communication throughout the nervous system.
When neurons repeatedly engage in this activity, the synapses involved become more responsive, and the connection between the neurons grows stronger. This phenomenon is called synaptic plasticity. This diagram on the right shows the difference between a normal synaptic link and a potentiated one. In a normal synaptic synaptic link, the synaptic cleft does not contain as concentrated number of neurotransmitters as the enhanced synaptic link. But why are neurotransmitters so important? These chemical signals allow messages to be sent between neurons, a connection that allows memories to form. The more concentrated the synaptic cleft is with neurotransmitters, the stronger the memory. Therefore, when the synaptic connection is potentiated, it keeps firing repeatedly, releasing higher amounts of neurotransmitters and strengthening the memory. Therefore, the normal synaptic link doesn't have as concentrated number of neurotransmitters as the potentiated one. But how does this relate to the Hopfield network? Well, the Hopfield network uses artificial neurons to mimic behaviors of neurons in the brain, therefore being able to complete the same task. This famous math equation, called the Hebbian learning rule, represents how the Hopfield network stores memories by figuring out how artificial neurons work together to remember patterns. But why does this equation allow memories to be stored?
In order to understand this, each part of the equation needs to be understood. M1 represents a column vector. A column vector is a vertical list of numbers used to represent memory patterns, where on switches are shown as 1 and off switches are shown as -1. On means that the specific part of the pattern are being expressed, therefore allowing a pattern to form, and off means that parts are being repressed. Together, these values form a pattern that can be stored and recognized by the network. These column vectors can represent memories as they produce patterns.
However, to store a memory pattern, a matrix needs to be formed, as shown here in the picture. To do so, M1 needs to be multiplied by its transpose, M1t. But what does it mean for a vector to be transposed? This means the vector is being flipped from a vertical column to horizontal row. A matrix is formed by multiplying the column vector M1 by the row vector M1t. This multiplication creates a matrix. These rules apply to M2 as well. These matrices are added together to create the weight matrix. This square matrix stores the strength of connections between artificial neurons, encoding the memories into the network. This allows the Hopfield network to later retrieve the stored memories from noisy or even incomplete inputs. It is also important to note that in this equation, only 2 memories are being demonstrated. However, an organism's brain and the Hopfield network can store much more than 2 memories simultaneously. Now, you probably saw the quote underneath the title, "Neurons that fire together, wire together." What does this mean? Well, this means that when 2 neurons are active at the same time, their connection strengthens. This forms the basis of the learning for the Hopfield network.
Now that we learn how to store memories, how do we recall memories? The answer to this would be through gradient descent. When recalling a memory, the process begins with a noisy or incomplete version of a stored pattern and set that as the network's initial state. The network then uses the weight matrix created during the storing process to update neurons one at a time, each neuron calculating its new state based on the weighted sum of inputs from all other neurons. With each update, the network's energy never increases. It either decreases or remains unchanged. The iterative process continues until the network reaches a stable configuration, or an attractor, where no neuron wants to change its state. This means the energy is at a local minimum. The final state is the stored pattern that best matches the initial cue, effectively reconstructing the clean memory from the noisy input using pattern completion.
In this example, it is shown that through a Hopfield network simulation, which turns the theory behind Hopfield networks into a working program. We stored 2 memories of facial expressions, as seen on the left, a happy face, and on the right, a sad one. The happy expression in mathematical terms would be represented by a column vector to the network, the sad facial expression represented by a separate vector. Then, in order for the memory to be stored, it is stored as a matrix. The sum of the matrices create the weight matrix, which guides the network to recall the correct base when given a partial or noisy version.
This is an example of how we recall images. As seen in the image on the left, we have replicated a noisy or incomplete image. This input is the starting point in the process of recalling a memory. As the image keeps updating itself with each iteration, it becomes more stable and loses more energy. Once it reaches a low energy output, or the final value, through convergence, it successfully recalls the memory. The final value is represented on the right.
In this example, we've shown how memories are stored and recalled within a storage system of 2 memories. It was also explained how the network can store more than 2 memories. But how many memories reaches its maximum?
The mathematical expression for the maximum capacity of neural networks are represented by 0.4 times n representing the number of neurons or units in a network. The graph can be used to explain why there is a maximum number to amount of memories that can be stored. The graph's alpha axis, as shown, represents the amount of memory stored in the system, T representing the temperature. Temperature in terms of the graph means the amount of noise the network emits. Analyzing the graph's trend, it can be seen that the more memory stored, the more noise is emitted, and the harder it is to recall stored memories.
Alpha, shown in the graph as A, is called the memory load. This shows how many patterns are stored per neuron. To calculate, the formula P over N is used, P representing the number of stored memories and N representing the number of neurons. But how does this memory load affect the way information is stored and recalled in each section of the graph? As shown, the graph is divided into 4 sections, A, B, C, and D. In section A, the least amount of memory is stored is allocated. Here, the noise is also reduced, and the state at which the memories are stored is illustrated in Model 2. Model 2 shows how memories can be stored in a stable state. In the model, points represent memories. However, as the amount of memories increases, the noise increases as modeled in sets A, B, C, and D. B, C, and D, not A. The stability of the memory is decreased, and a decrease in stability makes it harder to recall, eventually reaching a maximum in the number of memories that the network can store. Alpha C, as seen in this graph, represents the maximum point of memories on the model, the graph. And if it cannot go more than this. This is the maximum amount of memories that can be stored.
We've probably focused on networks that settle into a fixed stable state to store patterns. Now we have decided to explore networks that generate sequences of patterns by allowing pattern transitions in the connectivity. This means that in some brain-inspired networks, instead of staying fixed in one pattern, the activity can move through a repeating loop of states. This looping behavior is called a limit cycle attractor. As shown in the image, the patterns are moving from one state to the next, 1, 2, 2, 3, and so on. The system would be wired to naturally move from one pattern to the next in the cycle, instead of stopping at a single fixed state.
In order to do this, we would be using balanced connections and directional connections. Balanced connections are when signals being sent and received are equal in the neuron, keeping its activity stable. Balanced connections would be used for the network to learn the pattern individually, meaning in the image, it allows the network to learn the pattern 1 to 5 individually. Directional connections, signals that travel in one direction from a neuron to another, would be used to help the network transition from the one image to the next, allowing the loop shown in the image to transition from 1 to 2, 2 to 3, and 3 to 4, and so on back to 1. This is we're excited, and thank you for listening.
Excellent. Thank you. I should say Sammy and Amir were the youngest members in the boot camp. They're just in their 9th grade, and I'm very proud of you guys that you were able to follow the material, do a research project. By the way, Hopfield model is also very close to my heart because my PhD was on Hopfield model, and I studied how olfactory memory is stored in the brain using Hopfield models.
I have a question. I saw that equation capacity is 0.14 times n, number of neurons. How to think about this capacity? Is it a way to think about in megabytes, or how to think about this?
So it's the mathematical equation, not equation, but the mathematical expression that shows how memory can be stored. And for instance, if there was an n number of neurons, if you wanted to calculate how much memory storage there is, you would substitute it in the expression and find it. That's how it works, I believe.
Yes. Sammy, were you saying something?
No.
Okay. Yeah, so that's actually a great question. So imagine if there are 100 neurons, then that formula says that you store 0.14 times 100. That's 14 memories. You can store 14 memories in this brain, consisting of uh, 100 neurons. Each each neuron can have just two states, either 0 or 1. So each neuron can store just one bit. Okay. So if you can, and there are 14 memories. So 14 times 100, that is 1400 bits of information can be stored. Okay.
Oh, okay. So
Yeah.
you're saying 100 neurons times 0.14, so 14 memories.
Yeah.
And each memory is 100 bits, you said?
Yeah. Because yeah, there are 100 neurons and each neuron stores one bit of information.
All right, thanks.
So yeah, so this is the, just to be clear, we this is how much memories are stored in the Hopfield model. Okay, how much memories are stored in the brain, that is a separate question. And this model was proposed in 1982 as a model for how memories are stored in the brain, and it at that time it was not very biologically realistic, and for variety of reasons. But since that time, people have been working on it, including myself, to make things more and more biologically realistic. Okay, so so don't think that this formula actually is something indicative of how much memories are stored in the brain. But if you see online, if you see some numbers about how many memories are stored in the brain, like they have calculated it to be some trillion bytes or something, terabytes, then those numbers actually come out from the Hopfield model. Okay, they don't come out of neuroscience; they come out of the Hopfield model.
Thanks.
Is another question. Okay, so maybe I can ask a question. So, what do you guys think would happen if, suppose, neurons in in the brain or field brain start dying? What would happen?
I believe that if there's less neurons to be able to store the memories, like to store the memories in the Hopfield model, there would be less memories, or like less memories to be stored, or it's harder to recall because it's like unstable because some neurons might not be there, and yeah, that's maybe.
Yeah, and that is exactly what happens in Alzheimer's disease. Neurons start dying, and this model explains exactly how memory loss occurs once neurons starts dying. Okay, anyway, so Abhishek has a question. He says, is there a limit to memory storage of the brain?
Of the brain, I believe. So the brain and the Hopfield network, they work very similarly, even though maybe not exactly the same. So our brain does have a limit to the amount of neurons it has, and therefore it does have a limit to its memory storage. Because if it tries to store any more, it's like unstable and it won't be able to.
One other quick question. I found this concept pretty interesting. If I understood what you're saying is the reconstruction of memory itself is a neural network activity, meaning the memory is not. So typically, as an example, if we store something in a hard drive, we can retrieve it as it is. There is no neural network or no prediction involved there, right? What is stored is what is retrieved. But if I understood in your presentation, you are saying that memory is stored but retrieved in a neural network model, meaning it's reconstructed with some with, statistically with some probability of being correct. Is that how I should understand this model?
Um, Yes, so that is mainly correct. I believe that so what you're trying to say is that it's like getting reconstructed. Well, it's recalling the memory that it originally had stored based on the input you're given, that's being given to the network. It's recalling what it is. So I need to get back to you on that if it's completely reconstructing it, but I don't believe so.
Yeah,
I
also,
believe it's recalling.
I think Amaya is right. But I just want to add the way things are stored in computers, there's a separate hard drive where everything gets stored. That is not how things work in the brain. In the brain, the memories are actually stored across the whole of the cortex. Okay, so it's diffusely stored everywhere with multiple copies. So yeah, there's a big difference between the memory storage in the two systems. And yeah, you give some hints, and then from that, it is able to reconstruct the memories as Amaya and Sammy showed. If you show if you show two faces, a happy face and a sad face, and then you show part of the happy face, it is able to recall the entire face. Yeah.
Yeah, that's very, very interesting. Thank you.
Okay, so Naren asked, was this the first time how memory stored is understood? That's what fetched the Nobel Prize.
Um, so okay, so what is the first time?
How
What
memories are stored. Is this the first time how memories are stored in the brain understood through the Hopfield model? And is that what fetched them the Nobel Prize? It,
I believe the Hopfield model wasn't made during 2024, if that's what the question's asking. I believe it was made in the 1990s, somewhere there. Um, and that's how the memory was originally stored in the Hopfield network. That's how it was figured out. In the Nobel Prize, it was they used the Hopfield model for machine learning and AI in 2024, and that's why they got the
okay, yeah, so let me clear up something. So actually the model was given in 1980s, 1982.
momentum.
82. Yeah, so was this the first time how memory stored was understood in the brain? No, actually the neuroscience community already understood how it's stored. Okay, physiologically speaking, qualitatively speaking, they knew that the memories are stored in the synapses, as they also mentioned. And this fact, this was given by Eric Kandel, a neuroscientist who is still alive, late 90s. Um, and he got Nobel Prize for this, for figuring out that memories are stored in synapses in 2000. He got Nobel Prize in 2000. He discovered it many decades before. What Hopfield model brought in was a mathematical model of neural network, which is storing uh, memories. Okay, a mathematical model based on neural networks. Okay, so we can be quantitative about how many memories can be stored, at what rate our memory is being learned, things like that. Then, so that's the history part. Then you ask, what is that? What fetched the Nobel Prize? So the Nobel Prize last year was actually given in physics for the Hopfield model, not in neuroscience but in physics. And the reason for that is, along with Jeffrey Hinton. So historically, what happened? This model was given in 1982. This inspired Jeffrey Hinton to create what's called Boltzmann machine. It's something which is no longer taught in taught in.
Got disconnected.
Oh, no worries, no worries. Yeah, so Hopfield model inspired Boltzmann machines, which in turn inspired deep learning. Okay, so that's the sequence. So nowadays nobody uses Boltzmann machine, but that was the original inspiration for all the deep learning networks uh, that were there. Okay, so I hope this makes sense. So Hopfield model has been doubly useful. On one hand, it has it was stimulus to create deep learning. Nowadays and AI. So nowadays people have figured out that Hopfield model in its more modern form, what's called modern Hopfield network, is actually directly equivalent to transformers, which are at the beating heart of deep learning models now, transformer architecture. So that's the AI side. The On on the neuroscience side, people have also made progress and made things, made Hopfield model a lot more biologically realistic. Okay. Um, so it's so a lot of different people study this network from different angles. Ameya and Sammy studied it from a neuroscience angle.
Got it. So its inspiration for neural networks and deep learning is what actually made it.
Yeah. Okay, so